I am Patrice Christman. Carlo has already introduced me. I'm a geologist specialized in mineral raw materials, minerals economy, minerals policies. I am working with the French Geological Survey. I have a lot of involvement also in European affairs, participating closely to what is called the Raw Materials Initiative and derived developments like the recently launched EIT Raw Materials. I'm also a member of the International Resource Panel of the United Nations, which is the equivalent for natural resources to the Climate Change Panel, which is certainly very well known to you. Minerals are essential to life. Don't say that you are against minerals and the minerals industry, because then you deserve to be nude, freezing in the dark, because minerals are everywhere around us. We all need them, and our lives are depending on them. So I'm trying in a short while to introduce you some of the issues that you are going to face and the kids you are teaching to are going to face in this most challenging period for humanity, that is between now and 2050. You will see why, especially 2050, because let's hope, let's cross fingers, I won't be there to see it, but you will be, and the kids you are responsible of will see it certainly, that hopefully human demography will stabilize somewhere around 2050. That would be a very good news for this planet, but we are not there yet. And always think that 2 billion people extra are going to be born between now and 2050. And you see the problems we have already in this pressure cooker called Earth nowadays. And add 2 billion people to the pressure cooker, and let's hope the pressure cooker is strong enough to not explode. So, that's a brief outline. I will briefly introduce the modern situation with metals and minerals, and the minerals boom we are experiencing since the early 20th century. The demand drivers, I will say a few words about the circular economy and the need of a transition towards a circular economy and what actually a circular economy is, and draw some conclusions. I have to go quite fast. You'll have the slides, and I'll be available during the coffee time for questions if you wish to have a private chat with me. This is where we were standing at the times of our arch-grandparents, early 20th century. At that time, developed countries like European countries, the US, people were essentially using, say, very broadly speaking, 10 metals and minerals. So we had iron, steel, we had a bit of copper, of course silverware, a bit of gold in the wedding ring, and a few metals like that, but not that much. Nowadays, we are using almost every element in the Mendeleev table, and that is something of great importance. You see this transition. Each of these elements here, that's just for the energy sector, has a use either for the production, the storage, or the distribution of energy. And I could explain you in detail those things, but that is just what we need for energy. Then you could add transportation, you could add agriculture, you could add health, you could add aerospace, you could add defense, and so on, and you would cover the whole periodic table of elements. That is how the production of metals has changed from 1900 till nowadays, 2015, and how it is likely to progress towards 2050. So the first thing is, if I look, that starts 1919, because that is from USGS data series 140, where you can find yourself the detailed data underpinning that diagram. So between 1919 and nowadays, taking into consideration 14 raw materials like iron, copper, zinc, lead, and so on, the world population has grown by a factor of 5, but our mineral consumption and metals consumption has grown by a factor of 20. So that means each people on Earth, in average, uses 5 times more minerals and metals in tons as compared to the early 20th century. And the growth rate over that period is roughly 3% per annum. So if you extrapolate at a 3% per annum rate, that diagram, that curve, that is the right side of the diagram, you will easily realize that we will have to produce more minerals and metals between now and 2050 than what has been produced in total since the onset of humanity. And that is an absolutely formidable challenge. It's a challenge for geoscientists because they have to find the deposits, which is not a minor challenge. It's a huge quantity of ore that will need to be found. And it's a challenge for environment because a lot of energy, a lot of water will be required. A lot of emissions will happen if nothing is done to curtail these emissions. And you will see later on that whatever you do with recycling, because some people will say, oh, recycling is the solution to the problem, let's recycle everything. Yeah, you will see that recycling is very desirable, it's very positive, it has very strong environmental benefits in terms of energy needed, for instance, to recycle. You need 10% of the energy to recycle aluminium from, say, aluminium cans. Then you need energy to extract aluminium from its ore. But nevertheless, in terms of demand for primary materials that you extract from the subsurface, recycling has a very limited effect because we have demographic growth and we have changing lifestyle. So that is a diagram on the world demographic evolution. That is a United Nations forecast scenario, not a forecast, sorry. Those are scenarios, stories about possible futures, not forecasts, of what may happen until 2300. So you see three scenarios, and the medium scenario, that is the horizontal line, it shows a stabilization of humanity around the 9 billion level until 2300. So if that happens, there's a strong message there. That is, if your generation imagines the solutions, the governance solution, the technological solution that will help to overcome the period till 2050, then humanity may enter into a golden age because you will have designed the solutions. And then with the stabilization of demography, things will be much easier. But the challenges till there are absolutely formidable. One challenge first is, for instance, the difference of metals intensity between the richer countries and the poorer countries. The blue part here shows the quantity of aluminium, copper, iron, steel, lead and zinc per capita that is used in rich countries like Europe or US, Japan. And the black part down is the same per capita amount in poorer, less developed countries. And to keep the long story short, you will notice that the gap here is a factor in average of 1 to 10. That means that as soon as poor people emerge out of sheer poverty, what will happen? They will engage into more material intensive lifestyles. That is, a man who is too poor to offer himself a bicycle, as soon as he has the resource, he'll buy a bicycle. The one who has a bicycle will buy a motorcycle. The one who has a motorcycle will buy a car, and so on and so forth. Notice that China has taken out of poverty over 300 million people in a very few decades, with a huge effect on demand for natural resources, not only for minerals and metals, but also for, say, bioresources like food, because the feeding habits of Chinese are changing. They're moving towards meat, and meat means a lot of water, for instance, but that water resources are another topic. To give you a few ideas, you will say, oh, bloody hell, I want to talk to anybody in this dark, messy, dirty raw materials industry. Not in my backyard, not in my lifestyle. These people are just polluting and destroying the planets. But please, you are raising here a camera. That camera has something like 40 different minerals and metals in it just to walk. And those have to come from somewhere. So here you have what is, it gives you an idea of what is in a cell phone. So in each cell phone, a smartphone nowadays, you would have about €1 worth of minerals and metals. A tiny bit of gold, a tiny bit of palladium, a tiny bit of cobalt, a tiny bit of lithium, and so on and so forth. There are some 40 elements in it. Altogether was €1. That's not much, but if you take the 5 billion, which is an estimate of the stock available currently on Earth of those smartphones, then you realize that there is something like 1/3 of a year of the global palladium production stocked just in our smartphones. That's a huge amount of metal. Of course, it's spread all over the place. One issue, if you want to recycle, is how do you collect these? How do you bring that stock that is spread all over the place back in, concentrate the flow so that it can go to a practical smelting plant where it's recovered. Any modern car, even the cheapest, smallest car, nowadays is full of rare metals. That is to show you where rare earths are in an ordinary car. Ordinary cars nowadays are full of small electrical motors for the, for the wipers, to lift the windows and so on and so forth, for the assisted steering. All these micro motors rely on permanent magnets made of neodymium, iron and boron. Neodymium is a rare earth element. If I take a modern aircraft, that is the Airbus 380, certainly a jewel of European technology and know-how, and I look here for a very rare metal, which is beryllium. Beryllium is produced worldwide roughly 400 tons per year, so it's one of the rarer metals. There are over 3 million terminals. These are small copper beryllium sheets that are inside the connectors, because modern aircraft is fly-by-wire, you know. Modern aircraft is a computer system with wings, so everything is connected there and everything goes by computer. So when the pilot pushes the engine, in fact, it transmits electronic bits to the information system and distributes them through the aircraft. So you need connectors to bring all this wiring together. There are 400 kilometers of wire in an Airbus 380 in order for the aircraft to work. And those connectors need to be totally free of oxidation, and the only way to have that guarantee a material free of oxidation in those connectors is copper beryllium alloy. That is not the map of the Vienna public transport system. Looks a bit like. That is the average composition of the hot part of a modern jet engine, again for aircraft. That is a slide from Rolls-Royce. And you can see those are different elements in the alloy, in the hot part of the engine, with titanium, molybdenum, copper, chromium, rhenium, ruthenium, aluminium. And the mix of those alloys is constantly evolving as material scientists try constantly to improve the working conditions of the modern jet aircraft turbines, because what's the rule of the game here is to get a temperature, an operating temperature as high as possible, because thanks to the law of thermodynamics, if you have a high combustion temperature, you have an optimum use of the energy in the kerosene, and you save energy. In other terms, you use less kerosene per mile. So, but having higher operating temperatures means that you have to have very sophisticated alloys to resist these extremely high operating temperatures. And here research and innovation is constantly progressing. Renewable energies, the talk of the day. I hear a lot about renewable energies as being the future for humanity. Okay, fine. The point here is that, yes, renewable energies are very good, they are very valuable, but they will need a lot of metals. That's the bad news. And that is just here to show you what's this requirement in steel. That is in tons per megawatt of installed generating capacity. So if I take hydropower, a hydropower plant would take something like 30 tons of steel per megawatt of electricity generating capacity. And you see how the curve goes up. Wind turbines use something like 150 tons of steel, 5 times more than a hydropower dam. Or concentrating solar panels. You see these huge solar farms. For instance, in Spain, there are some very interesting big solar farms. Spain is very advanced in that field. So there's a lot of mirrors, either with a circulating fluid inside the mirror, it's a parabolic mirror concentrating the solar rays towards a tube where fluid is circulating to collect the calories, or it's mirrors that send the sunshine back to a tower where you have a boiler and which then generates the electricity. So that is a lot of metal because you need steel and preferably stainless steel to resist corrosion to build all these huge fields of mirrors, and you need also extra rare metals. To keep the long story short, because I should stay within my time, the consequences of modern technologies, and especially of the shift towards renewable energies, is a very strong demand for metals. Here you have what's called the compound annual growth rate of the production of different metals. Many of them are used in the energy sector, and gallium, for instance, is gallium arsenide in photovoltaics. It's not the only use of gallium. Gallium is also used, you know, LEDs. LEDs, the light of LEDs is generated thanks to the quantic properties of gallium arsenide. So you have here extremely strong growth rate, and you see the blue bars are the average growth rate in percent over the last 10 years, and the yellow bars over the last 30 years. You see that in most cases, not in all, but in most cases, there is an acceleration of growth, of production growth over the last 10 years compared to 30. But you have growth rates that in general are close to 5% per year or well over 5%. If you extrapolate this over 40 years, you can realize that there's an enormous demand for metals. And that is again, despite whatever progress you can do with recycling. So a few words about the circular economy. So a circular economy, that is the way we think about it and we dream of it. That is an economy where there would be no more input of resources, no need for resources. You use waste as a resource. And you think that just the waste, reusing what is in the waste in end-of-life products, for instance, or in emissions that you capture, you can remanufacture and you can go on with that circle. That doesn't work because just because of the law of thermodynamics, you will constantly need to add energy to the system, first of all. And as I mentioned, we are in a context of demographic growth and of changing lifestyles towards more materials-intensive lifestyles. So you'll need to input more metals and minerals. So now the good point here is how do we reduce, there's a laser pointer here, yes. How do we reduce the inputs of energy, of water, of lands, of chemicals? We need to mine, to process, extract the metals from the ore. How can we reduce the outputs, the emissions to air, to soil, to water, the solid waste from that process? And how can we reduce in general the outputs also at the life phase? For instance, a car generates CO2 emissions, or a factory sends out dust, CO2, sulfur, nitrogen, whatever. So one very important concept, and I should improve that slide a bit further, is that outputs here and here could in many cases be used by other industries. For instance, if I generate sulfur in my process, sulfur can be turned into sulfuric acid and can be a valuable input for a fertilizer plant. So putting different type of factories all together in what's called an industrial park, an eco ecological industrial park, I could develop eco-industry, and that is making things happen in a way that the emissions and the waste from one industry serves as an input for another one. For instance, many industries generate a lot of heat. That heat can be used for other purposes rather than sending it into the atmosphere and wasting it. Of course, there is a lot to do there, and here key driver is innovation, research, innovation, new technologies, and also governance. I insist on governance because it's your choices, my choices as individuals that are key, but also the way our governments behave, that is public governance, and the way corporations, businesses behave. So we need the 3 levels of governance. We need to improve that. Public governance, individual governance, and the industrial governance. Recycling. Unfortunately, there are some problems with the colors, which are not exactly true. The colors in my presentation are a bit different. So what is dark here should be red. So imagine it's red. All those elements here shown in black are elements where the current recycling rates are less than 1%, despite all the technological prowess. The good news is we already recycle at a very high and efficient rate a number of common metals like copper, aluminium, steel. There we have recycling rates that in some cases in Europe are very close to 90%. Lead, for instance, is recycled 90%. The European collection system of spent car batteries and recycling car batteries is very good, very functional. But we have a big problem with all those rare elements, like rare earths, for instance, which we have in a small quantity in the products. We are not able to recycle them efficiently and certainly not economically nowadays. Here, that is to show you the effect of recycling on demand. If I take, if I consider the blue curve, the upper curve here is the demand, plotted demand growth up to 2050 with a demand growth rate of 5% per annum. Now I have developed 3 scenarios. One scenario where a product has a 5 years lifetime before being available for recycling. Say a smartphone, for instance, has only 2 years in average life cycle, because after 2 years, whoa, there's a new one. Let's look for Apple 6. I just had a 5. No, that's no good. So put them in the drawer and okay. So. But many products have rather 5 years lifetime. Your wash machine, your fridge, and so on have 10, or your car is even a bit more than 10 years. And a windmill, solar cells, and so on, copper in a building have 30 years and much more. So these 3 scenarios. So the first thing is during the 5 first years, here nothing will happen because the product is in use, or 10 years the product is in use, 30 years. So it's only after 5, 10 or 30 years that some flow available for recycling will happen. If I take a 50% recycling rate, which is an optimistic vision for many of those rare metals, which I told you it's less than 1% recycling rate nowadays. So if I take a 50% recycling rate, that is the amount of recycled, this green curve, which I will have available. And in fact, it's the black curve. That is the material flow available for recycling. And the green curve is the resulting demand. So, in fact, I am shifting the blue curve towards green. In other words, I am buying a bit of time, that's all. And that time, of course, shortens very much as the lifetime of a product increases. So if I have 30 years lifetime, that is, I will gain only a few months in demand. If I take, because the copper, I told you copper, we are recycling copper nowadays very efficiently. But that is copper that has been produced 50 years ago. Because sometimes I say jokingly, look, I have good news. We are going to blast this building this afternoon so we can recover the copper that's in the walls. Nobody likes the idea. They will wait probably for an extra 50 years or 100 years before this building will be dismantled, and then they will recover the copper so I can go back with my explosive and not blast this building this afternoon. Other problem with recycling is the complexity of our modern products. If I compare a natural ore is pretty simple assemblages. If you look under the microscope, some of you are geologists, you know, okay, they may look a bit complex, but they're not that complex, natural assemblages. And in an ore, you'll get 5, sometimes 10 different metals. You'll have 1 or 2 primary principal metals, and the rest are trace metals. If you look to a modern, if you look to a modern motherboard, the motherboard of your computer, the motherboard of your tablet or of your smartphone, you will first not realize, but there are 40 and more elements there. Very, very complex assemblages with varnishes, solder, all kind of things. So there's extremely complex assemblages, which makes it very difficult to recover the valuable elements that they are there. For instance, one of the big headaches is tantalum. Tantalum is a very rare metal. Tantalum is produced essentially nowadays in what's called the Great Lakes region of Africa. That is the eastern part of the so-called Democratic Congo Republic and Rwanda, Burundi. That is a zone sadly known as a zone of terrible conflicts, which are the most deadly conflicts on Earth since World War II. Over 2 million people already died in this region for conflicts. And part of these conflicts are driven by the availability of tantalum ore. It's a very valuable ore, which is easily exploitable by local people. They are extremely poor. They are controlled by warlords, and they extract that ore, coltan, to feed the industry. Of course, now, thanks to the Dodd-Frank Act in the US, and a general move of the industry, there are now a traceability of that mineral that has been put in place, and so-called conflict-free certification, because some mines are operating according to clear, verifiable human rights standards, but some are not. And so that tantalum ends up in tiny microcapacitors that are on that motherboard. Each of these capacitors has the size of, how you say, a pin. You know, the kind of thing you use for embroidery. So it's a tiny thing. Yeah, it's the not a needle, it's the pin with a round, spherical head. Yeah, so it's something like 1 millimeter or 2 in radius, not more. So there are a few milligrams of tantalum in each of these capacitors, and nobody has found so far the economic process. There are technologies available, but the problem is the economy, how to economically recover those few milligrams in each of these capacitors. So conclusions is really, you ladies and gentlemen, I'm very excited to be with you. I'm very grateful for the invitation, and I'm very happy to address you, because your role is absolutely essential to pass on the message. I say I'm personally very involved through the UN system with sustainable use of natural resources, and I will provide you access to our panel website, where you can download a number of reports. So sustainability issues are central to the future, and you have a great role. I think education in the sustainable use of natural resources need to start at the youngest age, and it should be a very central component of our societies. The problem with our societies, I see personally, is that on one side we want brainwashed consumers able to buy whatever junk the economy can put at them. And on the other hand, we want well-educated, well-aware, well-awake, responsible citizens. I see a problem there. You hardly can be the two at the same time. Science-based education, not emotion-based. Our world is full of emotions, and those emotions and values and beliefs and so on are leading us to a chaos. So we should come back to facts and findings and solid science. Education in resource-related issues, sustainable management of these natural resources, not only minerals, water, soils. If somebody asks me what is the most important natural resource in my view, I would say soil. Because soil is a very limited amount. We can count the amount of fertile hectares of soil available on that planet. And soil is food. Soil is clean groundwater. Soil performs many, many functions. I'm not going to start now a conference on soils, but but it's a very important issue. So in general, natural resources. Research and innovation is needed. That is a key to the future. If I would have given the same presentation at the early 20th century, looking at what the future of the 20th century would possibly look like, I would say, oh, look, we are going to need more minerals than what has been produced since the onset of humanity. That was equally true at the early 20th century. And I would say, whoa, fantastic challenges in front of us. And finally, we're here. We have produced all these minerals. We have not yet destroyed fully the planet. We are constantly working at it, but we are not. Still, there are rooms of hope. So I think that the power of imagination, the power of creativity of mankind, the goodwill, because there are negative sides in humanity, but there are also very positive sides. So I think still there's much power for innovation, imagination, and so on. And finally, it should be knowledge-based natural resources governance. I insist on the importance of individual choices, individual informed choices, and your role is to inform yourselves and to pass on that information to the kids and the young people you're in charge of. You have a wonderful job, and that has to be developed, of course, at the broad global level. If just we Europeans are cleaning and tidying our place, that is not enough. That is the whole world that has to engage in that process, obviously. And that should all be based on transparency and accountability. And so good luck with it, and hope to see you maybe in 2050 from my graveyard. You'll provide me good news that you have managed. Thank you.